we're going to be learning several different ways that we can classify acids and bases. But historically, acids were based on whether something was sour tasting or not. So even though in lab we tell you not to taste things, right? The original chemists, at least those that survived, tasted things and they smelled things and they did all sorts of stuff that we shouldn't be doing today. But one of the original definitions of acids, and I think this probably comes from some Greek or Latin root, is that it's sour tasting. Acids tend to be sour. And bases are just things that will neutralize acids. When you add a base to something that tastes sour, it no longer tastes sour anymore. So bases neutralize acids. But they didn't really understand, what was going on at a molecular level. Now we have a much better understanding of what's going on with acid and base neutralization. And so we can now think of the term neutralize as we're actually neutralizing charges, right? Acids and bases in solution, they have positive and negative charges. And when they neutralize each other, they're going to, the charges will neutralize. And as you'll see in a moment, we're going to make some water when it's neutralized. Now, also on a historical note, things that were basic, right, that would neutralize these acids, they tended to be group 1 and group 2 metals. So bases tend to be group 1 and group 2 metals. All right, so these are the alkali metals and the alkaline earth metals. And because compounds with those materials tended to be bases, we also have a term that you probably all recognize. Alkali solutions are basic solutions. And that's kind of where the term comes from. So when you have bases that are made up of group 1 and group 2 metals, they form alkaline solutions. So alkaline is kind of synonymous with base. Now, in the classic acid-base neutralization reaction, hydrochloric acid, sodium hydroxide. This is the hydroxide polyatomic ion. So that's a classic acid and a classic base. You've used these all the time in labs. And when we neutralize an acid and a base like this, we tend to get two general types of products out. One of them is always going to be a salt of the acid, and the other one is water. This is the classic setup for an acid-base neutralization reaction. All right? We take an acid and we mix it with a base. You get a salt of the acid and you get water. The AQ, aqueous solution. And what does it mean when you're in aqueous solution? It's dissolved in water. Water is the solvent, and you have, in this case, ions are dissolved in water. Not always, but usually it applies to ionic compounds. Ionic compounds are going to dissociate into ions in solution because they're being stabilized by the ion-dipole interactions between the ions and the dipoles of water. What we do here on top, this is the molecular equation. And that's really a shorthand. It's showing if it's describing the chemical reaction, okay? But if it's an aqueous solution, we can write what's called the full ionic equation that shows us really what's happening in solution. So in other words, we've got HCl in aqueous solution. What that really means is we have hydrogen ions in aqueous solution and chloride ions in aqueous solution. Sodium hydroxide in aqueous solution, when we write it that way, what it really means, that AQ really means that we have sodium ions in aqueous solution and hydroxide ions in aqueous solution. Now we show that it forms the salt of the acid in the product side, so NaCl in aqueous solution, but that's really sodium ions in aqueous solution and chloride ions in aqueous solution. Now, one of the mistakes students usually make when they do this exercise is they try to break everything apart. And the whole point here is that we're only breaking apart things that are listed in aqueous solution, because that's what it means to be an aqueous solution. It's actually ions in aqueous solution. This is water. Water is not an aqueous solution. Water is the liquid solvent. So if it's liquid, it stays liquid. Gas, if it were a gas in our products, a gas stays as a gas. And if we were to form a solid, like if this were a precipitation experiment, a solid stays as a solid. The only things that we break apart are things that are listed in aqueous solution. Now, our molecular equation on top is already balanced. It just so happens that these are all 1-to-1 to 1-to-1 molar ratios. If we had different molar ratios due to balancing, then those I would carry those down into the full ionic equation as well. Or if I was breaking apart materials that had more than one anion or more than one cation in them, I would translate that down here as well. Okay, but this is just a simple example. We don't have that. So now that we see what's actually happening in solution, we then recognize that some things are reacting and some things are not reacting. So if you notice, we start with sodium ions in the reactant side, and we end with sodium ions in aqueous solution in the product side. They haven't changed at all. We also start with chloride ions in aqueous solution and end with chloride ions in aqueous solution. They're not changing at all. Even though it looks like everything's happening here in the molecular equation, in solution, the sodium ions and the chloride ions haven't changed at all. They start swimming around in aqueous solution and they end swimming around in aqueous solution. So they haven't changed one bit. So like in math, we can then just cancel them out. They're not really factoring into this balanced equation. And indeed, they're not reacting at all. These are what we call the spectator ions. They're not involved in the reaction. In this case, our spectator ions are sodium ions and chloride ions. They're here because what is reacting, as you'll see, is the hydrogen ions and the hydroxide ions. But you can't just go to the chemical laboratory stock room and find a bottle of hydrogen ions or a bottle of hydroxide ions. The way they get into this reaction is they are paired with their cation or anion partners, okay? In this case, the partners are HCl, or the partners make HCl and NaOH. But once they're in solution, the only thing that's really reacting here is what doesn't cancel out, what's unique on each side of this reaction. That's the hydrogen ions in aqueous solution and the hydroxide ions in aqueous solution. And they, when they're present together in aqueous solution, will combine and form liquid H2O. This is what we call the net ionic equation. And the net ionic equation, that shows you the actual chemistry taking place. Now, this net ionic equation, this applies to all sorts of reactions in aqueous solution. But this net ionic equation for acids and bases, this really is the heart of our discussion in chapters 15 and 16. Everything that we're describing that's happening with acids and bases in aqueous solution is really all boiling down to this equation. The amount or concentration of hydrogen ions in aqueous solution and the concentration of hydroxide ions in aqueous solution. This is what's ultimately going to dictate whether something is what we call behaves as an acid or behaves as a base. So ultimately, acids and bases are compounds that affect the concentration of hydrogen ions and the concentration of hydroxide ions in aqueous solution. All right, we're going to be talking about pH soon enough. pH is just a convenient way to describe the concentration of hydrogen ions and hydroxide ions in solution. The pH, that's going to relate to the hydrogen ion concentration. And something that you don't see often, but we'll talk about, is the pOH. That's just another way to describe the hydroxide ion concentration. We may talk about things as being acidic or basic. Those are just terms that we'll be using to relate the relative pH or pOH levels. We have different theories about acids and bases, and you can read about these in the chapter. There's the Arrhenius theory, the Bronsted-Lowry theory, and also the Lewis theory. This chapter spends most of the time talking about Bronsted-Lowry and Arrhenius. You'll be seeing Lewis theory for acids and bases more if you continue on to organic chemistry. But just to give you some simple definitions here, for the Arrhenius theory, it considers an acid as a compound that produces hydrogen ions in solution, and a base is something that produces hydroxide ions in aqueous solution. And by the way, I keep saying in aqueous solution, acid-base chemistry happens in water. It's all in aqueous solution. The Bronsted-Lowry theory is a little bit more specific than that, and that's because there are some materials that act as bases, but they don't themselves produce the hydroxide ions. They cause the hydroxide ions to be produced from the liquid water solvent. Okay, so a formal definition then for Bronsted-Lowry theory is that a Bronsted-Lowry acid is something that donates a hydrogen ion to the solution, and a Bronsted-Lowry base will be a material that accepts a hydrogen ion from the solution. And although we won't be talking about Lewis acids and bases much, let me just at least give you the definition for a Lewis acid and a base. A Lewis acid is something, now that has to do with the electrons. So the Bronsted-Lowry theory has to do with the hydrogen ions. The Lewis theory has to do with what is happening with the electrons. So a Lewis acid is something that accepts electrons, and a Lewis base is something that donates electrons. We're going to be spending our time talking about these guys. Okay, so acids and bases, these are the compounds. You put an acid in water, it's going to give it an acidic pH. Bases are things that you put them in water and they make basic solutions, right? That's not too much of a leap. Or again, another word for basic is alkaline. And I told you we're going to use pH to classify these. And we'll get into the math of pH in a lecture. But I'll just preview that. If you measure the pH, and if the pH of a solution is less than 7, that's what we call an acidic solution. And if you measure the pH of a solution and it has a pH that's greater than 7, we're going to call that a basic solution. That also then means that if we have a solution that's at a pH that's equal to 7, that's what we call a neutral pH. And I mentioned to you that neutralization, right, is now that we understand what acids and bases are, neutralization is simply the H plus and the OH minus neutralizing each other, the charges. If we have one H plus that meets one OH minus and they come together to form water, the plus and the minus are now neutralized, okay? So we call this neutral pH because there are no charges here. At neutral pH, we have a special condition where the hydrogen ion concentration is equal to the hydroxide ion concentration. That's why it's called neutral pH, pH 7. Compounds that are made with metals, and you put them in water, they tend to be bases. This is not absolute. They tend to be bases, like metal oxides and metal hydroxides and metal hydrides. What are those? A metal oxide. So you've got a group 1 or group 2 metal like sodium oxide. A metal hydroxide, well, you've seen one already, sodium hydroxide. There's also some metals that react with hydrogen to form what's called a metal hydride. Those are kind of interesting compounds because there the hydrogen isn't a plus charge. The hydrogen is actually a minus charge. It's not the hydrogen ion, it's the hydride ion. So like lithium hydride. And you put these things in water and they tend to form bases. If you take sodium oxide and you put that in water, or here's another one, magnesium oxide, and you put that in water. So these are solids. And you put this in water. So this is going to form the magnesium 2+ ion in aqueous solution. And now you've got oxygen there, but you're not going to have just oxygen ions in solution. The oxygen ions actually react with the water to form hydroxide ions, and you get 2 of them. Here, I'll even show that to you real quick here. So here's the oxide ion. Let me show you the Lewis structure for the oxide ion. Oxide ions are 2-. They've gained 2 electrons. So here I'm showing the Lewis symbol, I should say, for oxygen 2-. And you've got water. And we've already discussed at length water. We know that oxygen is very electronegative, right? So in these bonds, most of the electron distribution in the bonds are skewed towards the oxygen, leaving those hydrogens as slightly positive, actually more than slightly, because oxygen is very electronegative. So you've got these electrons on the oxide ion. They're going to come over and interact with the water, and they're going to steal one of those positively charged or delta positive hydrogens away. And that's going to give you basically 2 hydroxide ions. It started as 2- and H+, right? And then we steal one of the hydrogens away. Now we have 2 hydroxide ions, and each one of them is 1-. And look at what we've done. We've increased the number of hydroxide ions in solution. So by putting magnesium oxide in water, we're increasing the concentration of the hydroxide ions. So they're no longer equal. If we started at pH 7, where H+ and OH- were equal, and now we put a metal oxide in there, we're producing OH- in solution. So the pH we would measure is going to be greater than 7. Metal hydroxides do the same thing. That one's a little easier to describe. Sodium hydroxide, you put that in water and you get sodium ions in aqueous solution, and you get hydroxide ions in aqueous solution. So there you go. There's other compounds that don't have metals in them, non-metals. Those tend to be acids, like the non-metal oxides. And you've seen some of these, a non-metal oxide. CO2, carbon is a non-metal oxide, carbon dioxide. If you put that in, now that's normally a gas. If you bubble some carbon dioxide with H2O, liquid, you end up forming H2CO3. Very unusual. You might not have been able to guess that. This is carbonic acid. And notice I showed this with a half arrow because this is not a reaction that goes to completion. There's an equilibrium between CO2 gas and H2O liquid and carbonic acid that's formed. Now this is carbonic acid in aqueous solution. And when you have carbonic acid in aqueous solution, although it could go backwards to the left here, there's another equilibrium here that we can describe. And this is where carbonic acid will then decompose into a hydrogen ion in solution and the bicarbonate ion in aqueous solution. I wanted to focus on this one particular equilibrium because it's very, very important. It's happening in the environment and it's happening right now in your blood. In blood, this reaction keeps your pH levels at just around pH 7.4. Your blood doesn't have to get too far away from that pH value for you to be in trouble. Blood pH below 7.35 or above 7.45 and you're in the hospital. A bit more outside of that range and you're dead. In the oceans, a similar pH system is at play, and since it's related to the CO2 being dissolved in water, these reactions are also involved in climate change. That is, the ocean is helping a great deal as a carbon dioxide sink for all of the extra CO2 that has been pumped into the atmosphere pretty much ever since the Industrial Revolution.
But that also means that come the day that we stop producing so much excess CO2, and I hope that day comes very soon, we'll still have to wait for the oceans to give all that CO2 back. And again, that's going to be through Le Chatelier's principle and these equilibrium reactions. So this really is a reaction of life. You may think that the reactions of life are photosynthesis and cellular respiration, but this one is just as important. It keeps you alive. See you in lecture.
We're going to start off today just having a nice little thought process discussion on strong and weak acids and bases. But acids and bases are also things that happen in aqueous solution. In particular, we're going to be looking at things that produce hydronium ions in solution and hydroxide ions in solution. Okay, so I'll remind you of a few things that maybe I didn't talk about in the video. When we talk about strong and weak as terms, here they are defined for you. Usually, when you learned about this in Gen Chem 1, you learned about this in the context of electrolytes. And if you remember what an electrolyte is, anyone remember?
Things that completely disassociate?
Not completely, but that they dissociate. But dissociate into what? It's important. Into ions in solution. Because ions have positive and negative charge. All right, so they can conduct electricity. So they're called electrolytes. A strong electrolyte will completely ionize in water, whereas a weak electrolyte will only partially. And that's the only difference. If it's strong, it's just 100%, right? Completely ionized, it's about 100% dissociation. And if it's partial, it's just less than 100%. And here's a diagram of that. Here's two reactions. The reaction on the left, this is nitric acid. And on the right, this is nitrous acid. And I've labeled these things for you like hydrogen ion donor and hydrogen ion acceptor because I talk about the definitions of acids and bases in the video in the context of Bronsted-Lowry bases and Bronsted-Lowry acids. Now, as diagrammed, right, nitric acid will dissociate 100%. So here we have an arrow. This reaction goes virtually to completion. Okay, so we have an arrow that goes from the left to the right. And it dissociates into its ions. The nitrate ion, polyatomic ion, and the hydronium ion. Nitrous acid does the same thing. It dissociates into the nitrite ion and the hydronium ion. But this is less than 100%. So notice we have a reversible reaction here. It's less than 100%. One goes to completion and one goes to what?
Equilibrium.
Equilibrium, that's right. Which means just like what we did in the last chapter for equilibrium, we can describe this equilibrium with a KEQ. There's actually a KEQ for both of these. The equilibrium for the strong acid, well, it's virtually 100%. So is it going to be much, much larger than 1 or much, much less than 1?
Much larger.
Much larger because?
The product's favored.
Because what?
It's going to favor the product.
It's going to favor the products. And when you write the mass action expression, products over reactants, it's almost all products and almost none reactants. So KEQ here is huge. It's much greater than 1. Anything that's not strong, right, that dissociates less than 100%, is going to be classified as weak. And as you'll see when we get there, there's different levels of weakness. All right, and we can actually assess which one's weaker than another one in the whole context of them all being weak. But all weak means is that it's less than 100%. Doesn't mean it doesn't hurt you, all right? You can be hurt more by a weak acid than you can by a strong acid. It just depends. You know what it depends on? What?
Molarity and concentration.
The molarity. It depends on the concentration. That's absolutely right. So you can be hurt by like a 6 molar solution of a weak acid compared to a 0.0006 molar solution of a strong acid. All right. All strong and weak tell you is the extent of the dissociation. Here's KEQ. This is going to be less than 1. And as you'll see soon enough, we can also derive a mass action expression for these weak acids and weak bases. We can do Rice tables for these weak acids and weak bases and figure out what the equilibrium concentrations are going to be. And guess what? We're going to do all of that. Yay! All right, now here's some pictures from the textbook that just kind of show you in picture form that for nitric acid, which is a strong acid, it dissociates virtually 100%. So you've got basically all products over here. Whereas with nitrous acid, look at this, right? Here's the equilibrium, right? The equilibrium is far to the left. KEQ is less than 1. Now, why do you think that is? I mean, look at the materials here. This is HNO3 and this is HNO2. They're pretty similar. So why do you think it is? Why? Why is nitric strong and nitrous acid weak? Don't tell me. Why don't you guys discuss? Discuss amongst yourselves for a little bit. Just think about it. What's different? And don't just identify. I mean, it's easy to see what's different. I want to know why that makes a difference.
So it'll dissolve into the water easier.
I think it's because oxygen is really electronegative.
The oxygen is more electronegative. So why does that make a difference? Molecule listed up here, right? Here's your hydrogen. Whoops. Now remember, the hydrogen is what is being lost to the solution, why it's called an acid, right? So this is going off as a hydrogen ion, which is also the same as a hydronium ion. And if you want to know why that is, you got to watch the video. Okay? So when that hydrogen leaves, right, it's leaving its electrons behind. There's 3 oxygens there. One of them it's directly bonded to, but the other 2 are very, very nearby. And oxygens are so electronegative, they want to have those extra electrons that are in the shared bonds. All right, so it's withdrawing the electron density away from the hydrogen, and you've got one more oxygen there to do it than you have over here. But it's the same reason that they're acidic, but it also explains why one is more acidic than the other. To really explain that, we have to go back to effective nuclear charge and why things are more stable with I don't want to get into effective nuclear charge, okay? But because you've got the electronegative oxygens here, okay, there's 3 of them, the electrons, if just overall the system is more stable with all those electrons being distributed in this molecule around those oxygens where they are more stabilized by seeing a stronger effective nuclear charge around the oxygens. All right. Whereas in this case, there's only 2 of them, so it's just not as much. Now, you may be wondering, how am I going to know which one's strong and which one's weak, rather than just looking them up or Googling it. All right. And you won't know unless you look it up on a table or you Google it. But as far as the strong acids go, there's really only 6 acids that we consider to be strong like this. So it's easy to remember 6 of them. And I already told you one of them was nitric acid. So these are the strongs. Nitric acid, which is HNO3. There's hydrochloric acid, which is HCl. There's hydrobromic acid, which is HBr. There's hydroiodic acid, which is HI. So basically, the halogens
right? Except not hydrogen fluoride. That one's weak. So maybe if there's time, I might go into that a little bit, okay? There's also perchloric. Perchloric acid, which is HClO4. So it's perchloric, then there's chloric acid, chlorous acid, hypochlorous acid. You can read about those. That's in one of those slides in the very, very back. But perchloric acid is strong because look, it's got 4 oxygens here. Right? Chloric acid is HClO3, chlorous acid is HClO2, and hypochloric is HClO. So you can see the same trend going on there. Did I say 6? I meant 5. Oh, there is one more. There is 6. Anyone know what it is? Sulfuric, thank you. Sulfuric, which is H2SO4. Now, sulfuric acid's kind of interesting because look, there's 2 hydrogens there. And we'll be looking at that in a little more detail later. All right. It is a strong acid, but only for one of those hydrogens. All right, and like I said, more on that later. But everything else that you're going to see is weak. And how do you know it's an acid? Because it's called an acid. All right? So everything that's an acid has the name acid at the end of it. All right, so everything else is weak. And if it's weak, here's our molecular expression, all right? And we can write a mass action expression. We know what that looks like, right? That's the KEQ. But now we're going to call it Ka because it's the KEQ for an acid. Right? When you've got a heterogeneous equilibrium, we only put things in the mass action expression when the concentrations are changing. And what else do we have on the reactant side here? We have H2O liquid. And the concentration of H2O liquid stays the same. Doesn't matter how much liquid there is, a little bit or a lot, the concentration's the same. All right? So that's why I'm going to put it in here, but don't write this down in your notes, all right? Because if I were to include H2O liquid here, well, we don't. Because it's not changing. You can put that in your notes if you want. So you have to remember about heterogeneous. All right, so keep this in mind, the Ka, right, KEQ. If we're talking about the equilibrium expression for a base, we'll call that the K sub B, Ka, Kb. So none of this then should be new for you. Here's your mass action expression. This slide looks very, very similar. And here I have listed generic acid and generic base. So a generic acid we would write as HA. All right, here's the hydrogen that gets dissociated, and then the A is whatever else is left over. Okay, so if this is the acid, then here is what it looks like once it's dissociated. All right, we have the hydronium ion, and then whatever's left over from that acid, A minus. It was A, but what left was H plus. So all that's left is A minus. We're going to call this the conjugate of the acid. More specifically, this is the conjugate base of the acid. Okay? Now it's grayed out here, okay? But here's a generic base. Right? Definition of a base, Bronsted-Lowry definition of a base, it accepts protons from solution. So that base is going to accept an H plus from solution. So when it does, it looks like that, BH plus. It was the same base, whatever that is, but it's acquired a H plus, so now it's going to have an overall 1 plus charge from what it had before. So this is what we would call the conjugate acid of the base. Okay? Now, for the sake of this slide, I'm also showing you the base in this form. I'm showing it to you as A minus. It's the same thing, right? A minus
is going to accept a proton from solution and become AH. All right? So these two are the same, but I left this one dark because it now mirrors the generic acid. It's just in reverse. Okay? And that's because if I have a conjugate base of an acid and I run the reaction in the opposite direction, now that conjugate base is the base and the conjugate acid is on the other side, right? We basically work back and forth. Now, if it's a strong acid and the arrow only goes in one direction, then we can call it the conjugate base, but it never goes back because it's a strong acid. But in the context of a reversible reaction, absolutely. Who's the conjugate of whom is all dependent on which direction you're looking at the reaction. So really, it's better to just talk about them as conjugates. Now, if we do the mass action expression, here's the Ka for that reaction. Okay? And here's the Kb for this reaction. I just did it in the context of AH because I want to show you what happens, right? If we go back, if I were to flip back to that first slide where I show you the full ionic equation and the net ionic equation, all we're doing is we're putting an acid in solution, so it dissociates, and we're putting a base in solution, and it dissociates. But the net ionic equation tells us that the H plus is reacting with the OH minus, sorry. These two are reacting to form water in the end. That's the net ionic equation. So if we were to add these up, just take equation 1 and take equation 2, and let's add them up. So we take 1 and 2 and add them up and see what we get. So we have HA, aqueous solution, cancels with HA in aqueous solution here. We have A minus here, cancels with A minus here, and we're left with 1, 2 H2Os, liquids, are in equilibrium with the hydronium ion and the hydroxide ion. Which, if you go back and look, I mean, this is your net ionic equation. For acid-base reactions. But one of the things you were responsible for learning on your own last time was how you manipulate KEQ when you do, like when you run the reaction in reverse. KEQ is the reciprocal. When you add two reactions together, you multiply the KEQs. Right? This is Ka. This is defined by Ka. This is defined by Kb, which are written right above. So if I add these two together to get to the net ionic equation, we have to multiply Ka by Kb. So here I'm doing it. Right? I just took the Ka from there. I took the Kb from there, multiplying them. A minus cancels with A minus. HA cancels with HA. And what we're left with is the concentration of hydronium ion times the concentration of hydroxide ion. This is what happens when we do acid-base chemistry. Right? When we do acid-base chemistry, really all that's happening is the net ionic equation, which is really two equilibria merged together in the same reaction, so we end up with this mass action expression at the end. It's just the hydronium ion concentration multiplied by the hydroxide concentration. So we're going to put a new name for this quantity when we multiply Ka by Kb. We're going to call that K sub W. This is all happening in water, all right? K sub W. This is what happens when you have water, all right? Because it's just water. All that's happening here is the water is dissociating into ions. It may be easier to show it to you this way. If I took H2O and showed that it dissociated into H plus OH minus. It's the same thing. We just use hydronium ion because hydrogen ions don't exist as hydrogen ions in solution. They'll combine with H2O to make H3O plus.
If everything is canceling out, how does water by itself just magically?
Just magically. We're going to talk about that next. How it is that water splits off into this. It does, but very, very, very little bit. You've seen it the other way. We've talked about this reaction going in this direction. If you have hydrogen ions and hydroxide ions, they'll react together to form H2O liquid, okay? Let me emphasize this. Remember, showing the equilibrium back and forth arrows doesn't imply that it's to the same extent. All it implies is that there's an equilibrium. In this case, the equilibrium is all the way here, almost exclusively to the left-hand side. But there is a little bit of ions that dissociate, and we're going to talk about that in just a minute. That's the equilibrium. This is K sub W. This is for water. This is also called the ion product constant for water. Yeah, question.
Is it because water could act as an acid?
Is it because water can act as an acid sometimes? Yes. And water can act as a base sometimes? Yes. Water is, as we call, for those of you who watched the video, amphoteric. There it is. Water can behave as both an acid and a base. All right, so we're down here. Okay, so this is called the ion product constant for water, simply because it's naming what it is. It's the product of the ion concentrations. And we're considering it a constant because of how we're defining this. We're defining this under standard conditions, as always. For pure water, at 25 degrees Celsius, we can actually measure that the concentration of hydronium ion is 10 to the minus 7th molar. Now, written above is the net ionic equation in the context of water, but in gray, I'm just showing it to you just for a molecule of water that dissociates into its component ions now. Yes, this is an example of water behaving as a weak acid. But it's also at the heart of all acid-base reactions. In particular, these are acid-base neutralization reactions, is how we call them, because when this reaction runs in reverse, because it's mostly in this direction, okay, we're basically neutralizing the charges on the ions. That's why it's called a neutralization reaction. We'll just remind you that that's KEQ, okay? What's the mass action expression for this reaction? Well, you know how to do that. You take the concentration of the products, H3O plus times OH minus concentration, and you divide that by, in this case, the concentration of the reactants
Nothing.
squared. And wouldn't it be nothing? And why wouldn't it be nothing?
Liquids.
Because it's liquid, so we, in fact, don't do that. Okay? Because it's a heterogeneous equilibrium. We only put the things that are in aqueous solution. Okay? So, in fact, it looks exactly the same. That is the mass action expression. K sub W is the mass action expression for the self-ionization of water. Now, I told you this, all right? When we measure it, pure water at 25 degrees Celsius, the concentration is 10 to the minus 7th. That's 0.1234567. That's what that is, okay? Now look at this reaction. Look at the stoichiometry. What's the stoichiometry between the hydronium ion and the hydroxide ion? 1 to 1, okay? So if this is 10 to the minus 7th, what's the concentration of hydroxide ions? 10 to the minus 7th. Okay, so what is K sub W equal to then? under these standard conditions?
14.
10 to the negative 14th. I am not going to put all those zeros in. Okay? It's a ridiculously small number, right? Ergo, right, earlier question, I didn't know water split into its ions. Well, it hardly doesn't, right? But it does enough that if we start messing around, Le Chatelier's principle, okay, we're going to be able to use this and it's going to adjust. The equilibrium will adjust to compensate for when we add acids and bases. And we can measure that. We can measure it by measuring the concentration of the hydrogen ion concentration or hydronium ion concentration. And I bet you already know what terminology that we use to make that measurement. What's it called?
pH.
pH. All right. So what is pH? pH is just a simple way for us to work with these ridiculously small numbers. Scientists like working with just a handful of numbers, not all those zeros. Although we could just say 10 to the minus 7th. All right. But what we do instead of dealing with these small numbers is we're going to make a log transformation of that. All right. So we're going to take the log of 10 to the minus 7th. This is log to the base 10. You don't know how to do logs in your head? You can use your calculator. You'll be surprised. Why did I take my calculator out to figure out what the log of 10 to the minus 7th is? It's negative 7. All right, if you want to know the mystery of how logs work, all right, look that up on your own. Okay? But it's log base 10. So if the coefficient is 1, this is 1 times 10 to the minus 7th, right? It's the same thing. If the coefficient is 1 and it's a log base 10, then the log of that number is just going to be whatever the exponent is. And because scientists want to be working in positive numbers, I mean, we're optimists, we're not pessimists, so we want positive numbers, not negative numbers. We're going to take the negative log base 10 of the hydronium ion concentration, and that's going to be what we call the pH. Okay? So the negative log of the hydronium ion concentration, that's what we're calling the pH. It's just a negative log transformation. The P stands for the hydrogen potential or the power of H+, in case those of you are wondering. And if we were talking about the negative log transformation of the hydroxide ion concentration, what would you call that?
pOH.
The pOH. Very good. What if I took the negative log of the Ka? What would you call that? pKa. There you go. Mystery solved. Because now you know how Ka is related to an acid dissociating in water, all right? And that's going to give you a certain pH. If you know the pH, you're going to know what the pOH is, because this is always going to come out to be 10 to the minus 14th in the end. That stays constant. That's also why it's called a constant, all right? It's called a constant because it's KEQ. That's what we learned about in the other chapter. With Le Chatelier's principle, if we add more acid now, it's going to increase this, okay? But by the reversible reaction, Le Chatelier's principle, the concentrations are going to shift so that we have new equilibrium concentrations, but KEQ doesn't change. KEQ is always going to be 10 to the minus 14. So let me show you a few more tricks with these ideas. So I'm going to rewrite this, what I have up above, just so I can show you something. So let's take the K sub W, that's equal to the hydronium ion concentration times the hydroxide ion concentration, and that's equal to 10 to the minus 14th. Okay? Now if I take the negative log of the whole thing, since we know if we take the negative log of each individual one, we get the pH and the pOH and the pKa, right? So what are we going to get from that? We're going to get the negative log of K sub W is equal to the negative log of H3O plus times OH minus is equal to the negative log of 10 to the minus 14th. Right? Am I going too fast? Okay. Now, something you have to remember about about how logs work. I'll just put this one on the board, right? One of the identities of logs. We did this before. When you have, it was with natural logs, but it works with the same as with log base 10. The log, before we did like the log of A divided by B, that's equal to the log of A minus the log of B, right? Well, the same works here. The log of AB is equal to the log of A plus the log of B. There's other logarithm things that you guys should know about as well, but this is all that's important for now. So this is going to be the same then as negative log of H3O plus the negative log of OH minus, right? And so then that's going to be, so we've defined these things, right? The negative log of K sub W, that's going to be the pK sub W, which is the same as the pKa, but it's for water. Hold it. All right? That's going to be equal to negative log of H3O, that's the pH, plus negative log of OH minus, that's plus pOH, and that's going to be equal to the negative log of 10 to the minus 14th, which is what? Hopefully you don't need your calculator for it. 14. H plus and H3O plus are essentially the exact same thing. But the textbook goes out of its way to never use H plus. All right, so we've got a lot of equations here. I did a lot of derivation here, but let me highlight what's really important here that you're going to be using over and over again. All right? These, you're going to use over and over and over again. This, you're going to use over and over and over again. And this one, you're going to use over and over and over again. But you can see that they're all related. When I say you're going to use them over and over and over again, that's in the context of solving typical acid-base chemistry problems using pH. Right? All three of these are interrelated.